this term goes to 0, so you end up just balancing what comes in versus what goes out. So simply this plus this minus this is going to equal 0, which we expect that. So the same principle, and you can think of it as a simplified example, and we sort of mentioned it at the end of the class yesterday, or last time. So we have, this is our classroom right here, and we have 2 doors that people enter from, and we have 1 door right here. Okay? And think of it, we have 3 people are sitting inside the room already, and this is my control volume. I have 3 people that are going to come from this door, and I got 2 people that are coming from this door. And I got 5 people went out. Is that a steady state or unsteady system?
Steady.
Steady. Why? Because things didn't change inside. The 3 people are inside, they're just still there. And 2 that came in, conservation of mass went down. Now, what if only 4 of them came out? So most likely the mass that I have in the room changed. And that's where 4 of them stayed inside. So this principle represents this term. But if it stayed the same, if the people stayed the same, and it was only 3 that stayed there, it's steady state. And most of the time in our equations, we're going to simplify things for you. We're going to always consider the steady state-based system because it becomes complicated to look at the unsteady. But things are unsteady in nature. However, you can approximate things based on the steady state and get results accordingly. But I still have, how did you come to the conclusion that 5 come out if it's steady state? Well, I got M1, M.1, which is 2, M.2 is 3, and 5 mass has to be conserved, so therefore 5 have to exit if this is a steady state system. So it's making sense to you? The same principle will apply for conservation of momentum and energy. It's just conserve your quantity. In this case, it's easier because I'm identifying it by people, but from the force perspective or energy perspective or mass perspective, it's the same principle. I just need to conserve it, bookkeep it, think of it that way. So there's nothing complicated about it. All right, so conservation of momentum, which is, we said it's Newton's second law, so.
Can you pull it down?
Newton's second law, and we said, well, Newton's second law, the sum of forces is equal to mass times acceleration. Well, what is acceleration? It's meters per second. So, if I think of it from the derivative standpoint, it's simply the derivative of velocity over time. So, I can decompose my sum of forces, which we're going to talk about in a second, is equal to the substantial derivative over time, the integral of, this is just mass, so density, velocity, over volume. That's all it is. But all I did, because acceleration is a function of velocity, so this is volume, this is velocity, I'm just going to use u for here. This is volume. So this is velocity. And obviously rho is density. So that's my substantial derivative, and I'm tracking the mass as it accelerates or moves within that specific volume that I'm defining. So if I don't have the Reynolds transport theorem, which is not a conservation law like we discussed, how would I tackle this? Well, I have to actually bookkeep this. My control volume will be all of this. This is my control volume. It will be the people who are coming in, people who are here, and the people who are out. And the volume keeps as more flux. If these people decide to, there's another door that goes this way, so my control volume has to change as well. So that's, if I don't have the Reynolds transfer theorem, that becomes difficult from the propulsion perspective because we always have an inlet of some sort and we have an exhaust for thrust. So that's why we need the Reynolds transfer theorem just to convert our domain primarily. But it's not a conservation law. And I'm hoping this is ironed out for you that don't say Reynolds transfer theorem. Okay? And don't feel bad about it, like I said, because there's graduate students that the first thing you tell them what is conservation law is they say Reynolds transfer theorem. It's like, what? Okay. Sum of forces. What forces do I have to deal with? Well, I have different types of surface forces. Again, this is a recap of what you've seen before through fluids, thermodynamics, and high-speed aero, and things like that, but we're recapping it again. So we have pressure forces, we have viscous forces, we have probably external forces, and we'll talk about them in a second. So these are the type of surface forces, but we also have body forces. You know an example of a body force? Very good. And another example, you could actually apply it if the medium that you're dealing with or the fluid that you're dealing with can actually be manipulated through currents and whatever, so electricity and potentially change its characteristics, electric forces, magnetic forces. It depends on the medium you're dealing with. Bless you. Now, it depends on. So, how is useful this for propulsion? Well, we talked about different propulsion systems in general, and we said you need to find out what is your main mission with that propulsion system, and then decide what will fit best. So, I don't need a rocket for outer orbit if I am just moving or I need to get from one place to another at a low speed. It just doesn't help me. So the best way to tackle it sometimes is actually ionic-based propulsion. It's still mass. We still need to have a mass thrown to get a force, but we can do it through electrical current. And we'll talk about it closer when we get to rockets at the end of the semester. But, you know, that's why it's useful here, magnetic-based forces. If I don't need a lot of thrust, these are systems that might be helpful for me. But when I need a lot of thrust, there's different systems that I can use for that. Okay? Now, most of the time, given that we are dealing with fluids like in this room, it's full of fluids and it's light. So, accordingly, it doesn't have much of a weight to it. So I don't need to keep bookkeeping the gravitational body forces. So in general, we'll neglect the gravitational force or body force associated. So let's neglect body forces. Okay, so we'll focus on mostly surface forces. And the first surface force is pressure force. And that's simply pressure over integrated area. So if I want the force associated with pressure is equal to the integral of the control surface, and it depends on whether it's in and out. We'll draw it in a second. Normal component ds. So if I have this control volume that I'm defining, and I have a control surface right here, so this is ds. So if I magnify this, this is my control surface, and if my pressure force is coming out, that's why it's negative, and I have some kind of normal component n, so accordingly it's just the integration of my pressure over that surface area. So this is not new to you, and I'm going to write it right here. right? You're used to doing this. F is equal to P times area, right? So the area multiplied by the pressure equals the force. So it's the same principle. All I'm doing is putting it in an integral form. Why? Because, well, sometimes I have my area square, that area could change, that door could widen, so I need to account for these variations. Now, why is again important for propulsion? Well, you have geometries that change, CV nozzles that change, components that will change inside the engine that you're going to be tailoring as part of the propulsion system. So this is a variable for you. That's why we don't fix it. We use an integral-based form. But initially, we'll use it fixed in some of the problems. External forces. So what type of external forces do I have to worry about in propulsion? Most likely I have a propulsion system attached to a vehicle of some sort that I'm trying to thrust forward. So it is going to act backwards on my system in general. So if I have an aircraft wing, for example, you will find that the engine is actually attached to it like this. So if I do my control volume right here, so my external force happening right here. This is attached to that system. This is an aircraft of some sort. By the way, for people that are coming in, by this time we've already been done with the quiz, just to let you know. Just fair caution in advance. It will be the first 10 minutes within the class. We want to finish at exactly 45. We need to be on time so we could finish at 45. So these are the components of forces that I have to deal with as a reattachment. One second. Reattachment, and this aircraft of some sort has a drag to it. I'm trying to propel it forward. So the engine is producing thrust. It wants to move forward, but the aircraft wants to go backwards. And this is the force that is acting externally onto my engine. So by nature, for propulsion systems, we always have to deal with this because we have a vehicle or something that we're trying to move forward. So I had a question. Okay, very good. Another question. The FC, yes, this is the three components of the forces, right? So you have to deal with X, and you have to deal with Y, and out of the page is C. Now, most likely we're going to deal with mostly one-dimensional based systems just because it's easier to define the equations that way, but it's also, once you know the one-dimensional systems very, very well, you can extrapolate to the three-dimensional systems a lot quicker. Because, again, it's just bookkeeping at an additional dimension. If you know the fundamentals, which is these equations, these conjugations, these are your driving principles. Okay, any questions thus far? I want to keep the conservation equations in the same lecture because it makes sense when you see them together. If I split them up, you get lost, and that's how you say Brown's transfer theorem is my conservation equation. Because you need to see it together and visualize the whole picture. So it's to your benefit that I'm trying to do this. Questions on this? We're good? All right. So moving on. Well, what do I need to do? I'm going to keep it up here. Apply my Brown's transfer theorem. Apply it to what? To this, right here. So let's take a look at this. Brown's transfer theorem. Substantial derivative over time. Variable of that, v over time, rho u d volume is equal to, well, it's equal to my fixed control volume plus the rate of change, whatever comes in and out over the control surface. So I'm hoping that I'm too repetitive that you get sick of it. CV rho u d volume plus control surface rho v what goes in and out of my control surface. Now, what's different here was the V term. So think of your Reynolds transfer theorem. Where's the equation for that one? Bless you. Think of your Reynolds transfer theorem right here. So Reynolds transfer theorem, the V term here represents your actual velocity. And you still have to multiply by mass. Mass flow rate. Mass flow rate is rho u A. So A is your surface, rho u A, and B is your velocity. Now, why does this make sense to me? Why should this be correct? Well, we're talking about forces. And in terms of momentum for fluids in general, what is your general force or energy that you always will keep for fluids in general? What? Drag, but I'm looking for how do you relate it to an energy-based term based on velocity. So if I have an energy-based term, we're calling it energy, guys. Kinetic energy, half rho v squared. Right? It's an acceleration-based system. So that's your squared system. Half rho v squared. You don't have the half here, but it's rho v squared. So it's making sense to you, and that's the kinetic energy associated with the fluid. So now that we have this equation, we could go and actually apply the this essentially becomes our conservation momentum. Now, I want to rearrange, we said, let me get the equation again here, maybe this one. So, it's a sum of forces is equal to this. So, that means what type of two forces that we just highlighted? We said pressure forces and external forces. So let's just focus on those for now. Viscous forces are there, and they're present, and we have to account for them, and we account for them through efficiencies, actually. But let's focus on those two, because these are the critical forces that play a big role on my propulsion system. So this is this term. I have these two is equal to this. So if I say sum of forces is equal to volume, just writing again, volume plus variable control surface, rho u dot n ds. Well, I need to decompose the sum of forces. Well, I have two forces. I have pressure forces and I have external forces. So my pressure force is an integral over my control surface. So take this and substitute here. So sum of forces, which is equal to control surface minus P and ds plus, what am I missing? What is another force? It's an external force. Right? So I'm going to decompose it into a vector-based term, which I could have three components, but it's a vector force, is equal to partial T CV rho u volume plus CS rho u n ds. Okay. So I have my unsteady term, I have my external force, I have my pressure force, and I have what comes in and out in terms of the actual flow momentum. Now that's the key one, because that's what drives the thrust, by the way. You're going to realize this is really it. And your thrust is primarily v squared. That's that term. And you're mostly trying to accelerate this term. Okay, so if I am trying, and remember the classroom example when we just said people coming in and going out. If I'm trying to characterize a steady-based system, which term is going to go out? This term, right? The unsteady base system. So let's move everything else on the other side. and move this, keep it on the left-hand side. Why? Because I can cancel it out and say it's equal to 0.